Today we'll be doing chapters 5 through 6. And we're going to be doing question 1. So for part A, it's going to be asking us that pulling on a crate using a rope, except the rope is at an angle of 20 degrees above the horizontal. The weight of the crate is 325 newtons, and the coefficient of kinetic friction between the crate and the floor is 0.250. And it's going to ask us, what must be the tension of the rope to make the crate move at a constant velocity? So we have right here our crate, and we obviously have its weight, which is the force of gravity, and we also have normal force on it, and we have a kinetic friction force. But then as well, we have our tension over on this side. Now, we can lay over a bit of a XY plane over this, especially since we're working at an angle. So we're going to make this 20 degrees. This is just us just kind of see how this object will be moving. So we're pretty much pulling from both the X and the Y direction. Which means that we're going to be having sums of forces in the X and Y. Where we have sum of F in the X direction, sum of F in the Y direction. Now, for both of these, they do have two different ways. So see, there's different forces that are being applied to them. So in the X direction, we're obviously having our tension multiplied by the cosine of 20 degrees plus the negative, since it's going in the other direction, it'll be the negative frictional kinetic force. And since we're talking about a constant velocity, it's going to be equal to 0. And same thing here. Tension is equal to the angle, but this time it's going to be in the sine. Going towards y, 20 degrees. But it's going to be plus our normal force and plus our weight, which our weight is in the negative direction, so it's going to have to be negative and also equal to 0. Now we have to figure out tension, so we pretty much have to relate these two different equations that we have here. So first things first is that we can just say that t x direction is equal to, we can pretty much subtract this over this friction kinetic to the other side. And that friction kinetic is also equal to our coefficient, our friction coefficient, kinetic energy, multiplied by our normal force. So pretty much we would write that as tension of cosine 20 degrees is equal to the coefficient times normal. And then for sine, we're going to have tension of sine plus n minus w is equal to 0. Now, we can notice that our cosine, or our x values over here, have an n attributed. So we have n as well here in our y, and we can move everything to the other side. It's equal to 0, so it's much easier for us. We can then add our weight and subtract our tension times sine. So we'll have n is equal to weight minus tangent of sine 20 degrees. So then what we can do is then relate these two. Then pretty much have t cosine 20 degrees is equal to our coefficient kinetic multiplied by the weight minus our t sine. Now we can add this all. We can foil this to the other sides. So now we need to touch it on. And what we pretty much want to do, since these are subtracting by each other, that's fine. So let's have, forget that because we're foiling it. Should have the coefficient as well. So what we're going to do is we're going to add this over to the other side. We're going to add it over. Bt cosine plus the coefficient sine. Now, since these are being added together and we have t on both of the functions, we can take t out. So t can be on the other side, and then we can just divide all of this over to this other side right here, so that it finally singles out tension. So tension is equal to the coefficient or kinetic times weight divided by cosine 20 degrees plus the coefficient times sine of 20 degrees. So now we're just going to take our values that were given to us. So we know that our weight is 325. So 325 newtons multiplied by our coefficient, which is 0.250. And then we're going to have this over here, which is cosine 20 degrees plus 0.250 times sine 20 degrees. So let's take out our calculator. Now I'm going to put this all into one singular equation. So there, now our entire answer, pretty much tension is equal to 79.3 newtons. And that will be our answer for part A. So let's go on to part B. Part B will be much simpler. It's pretty much to be asking us what is going to be the normal force that the floor is going to be exerting on the crate. Now we know that we already got ourselves an equation from normal from as we were solving and pretty much getting C over here, where it's N right over here. N is equal to weight minus tension sine 20. So since we now have tension, we can now write our equation. So N is going to be equal to our weight, which our weight is 325 newtons, minus our tension now, which we now know, which is 79.3 times sine of 20 degrees. Same thing, but it's a calculator, so have 325 minus 9.3 sine of 20. And now our answer is going to be 297.8, but we're going to round that over to whole number 298 newtons. And that's going to be our answer. Okay, let's move down. Let's go to part C. So part C is going to be working similarly in the same way as part A, but this one we just have different values. It's going to be asking us, we're pulling a large box using a rope, except the rope is at an angle of 15 degrees below the horizontal. The weight of the box is 325 newtons, and the coefficient of kinetic friction between the box and the floor is 0.250. So we're going to figure out what is the tension in the rope to make this box move at a constant velocity. Now, let's draw this out right here. It's going to be very similar where we have our friction, our normal, our weight, and then our tension. Let's put on a little XY plane. Now, it's going to be different because we're moving 15 degrees below the horizontal. So it's going to be negative 15. Now, for me to simplify this, I like to have things in the positive direction. I'll do 345 degrees. I pretty much just get 360 minus 15. So we have this degree right here. Now, all these steps will be relatively the same of figuring out what our tension is going to be. It's going to pretty much just turn out the same equation. Because no matter what, tension is going to be equal to the coefficient times the weight over the cosine of our degree, 5, plus our coefficient, it's multiplied by the sine of our degree. Since that's pretty much what we worked out to ensure that t is by itself in the equation, this will always stay pretty true. So we just take our equation and then we're just going to substitute in what our values are. We have 0.250 times 325 newtons over cosine degrees plus 0.250 times sine 3.5 degrees. All right. So we're just going to do our math again. And instead of writing everything out, I can just go back, especially since we have a lot of the same values. Just re-edit this. So it gives me the answer that I want. So right over here is this equation, and it's going to be equaling to this number right here. So our total of force, tension, we want to equal to 90, we'll round it over to 90.2 newtons. So that's going to be our total force. And then for part D, which we'll put over here, it's going to be asking us what is the normal force of the floor exerting on the box, which is going to be pretty much the same thing that we just did as in part B. So our normal is equal to our weight minus t sine of theta. T sine of theta. So we know that once we substitute, normal is equal to 325 minus tension, which is 90.2 times sine of theta, which is 345 degrees. So let's do 325 minus 90 point. Just make sure I'm down there. 325 minus 9.2 multiplied by sine of 345. So our answer, we're going to round it over, we have 348.3. Our normal is going to be equal to 348 newtons. That's going to be our normal. Let's move on to part E. And here we're using a lightweight rope to pull a sled along the level ground. The sled weighs 485 newtons. The coefficient of friction force between the sled and the ground is 0.200. The rope is at an angle of 12 degrees above the horizontal. You pull the rope with a force of 150 newtons. Find the normal force that the ground exerts on the ship. So we're finding our normal force. Now, it's different wording as part B and part D, but essentially it's asking for the same thing, which is normal force. And it's already given us what our tension is. We know that tension, because we're pulling with a force of 150 newtons, that means that our tension on the rope will be 115. Let's diagram this out. First, here we'll have our dot for our sled. We have our normal force going this way. We have our weight going that way. We have our friction at F. Now our tension over this way. Just T. Since it's saying we're pulling, the rope is at an angle of 12 degrees. It's pretty much lower, but 12 degrees. Is that our XY plane lay over? It's saying that we're pretty much pulling the rope with 115 newtons this direction, which is our tension, and we have our X or Y. So it's asking us for pretty much the same thing, and we've worked out this formula before, where N is equal to the weight minus tension of sine theta. So our N is going to be equal to our weight, which is given to us as 485 newtons, minus our tension, which is 115 newtons, multiplied by sine of our degree, which is 12 degrees above the horizontal. Staying above it. So we don't have to do anything extra to make it seem how we want. So 485 minus 115 sine of 12. And that's going to give us, rounding over 0, our normal force is equal to 461 newtons. Go over to part F down here. Make sure it's visible. So this time, it's going to ask us for something new, which is we have to find the acceleration of the sled. And we're going to figure out if the sled is spinning up or down. So pretty much if it's going to be in the positive or negative direction. So what you have to figure out here is that if we're accelerating over here on our diagram, if we're accelerating and pulling towards this direction, that means our acceleration is going to be in our x-axis. So meaning that we're going to have to look for our net forces of x. So if we're looking for a net force of x, we have to include every force that might be within that net force. So we have friction. So I have our friction force, which is going to be equal to the coefficient for kinetic times normal. So what we're going to have to do is we're going to multiply. It's going to be our kinetic, which is going to be 0.200 multiplied by our normal, which is the weight, which is 485 newtons. It's going to be equal to 0.200 times 485, equal to 97. 0.22. Units. So then, afterwards, what we're going to have to do is then also find f of x, which is what is in the x direction that we're going here in our positive, what will be our forces there? And that's going to be our force applied times the cosine of our angle. So substitute over, force applied is going to be 115 newtons, tension times cosine 12 degrees. So 115 cosine of 12, we're looking at 112 point. Let's round this over 2.5 newtons. So we'll have those two there, and then since we have these forces, we're going to have our sum of forces in the x direction is going to be equal to first our f of x minus our friction force in the kinetic direction. So we're going to be having 112.5 minus 97 newtons. Zero. So 0.200 minus 97. I'm just going to go 2.5 minus 97. Just see something here. Times that. Take the wrong number real quick. I forgot to bring down this n right here. I was taking the weight. But this n would be our n that we're actually going to be using. So we're multiplying by 461 newtons. Because that's the n that we figured out for the sled. I knew I had done something wrong. 0.200 times 461 202. So then we have 2.5. 2.2. Yeah, okay, yeah, that's the right answer. So since we figure out our normal force from here, since we're pulling in our direction, that will also be pulling in our y, that will affect our normal force as well. Because the normal force is the force acting on pretty much the ground. As we have our sled here, it's moving in this direction, being pulled upwards. There's still going to be a normal force perpendicular to be pulling there. But since we're also pulling upwards, it affects what our normal force is going to be. So it changes our normal force. So when we're solving for our friction, we have to make sure that we use our coefficient times normal. So since we have a normal, do the coefficient times normal, which got over here, our E, would be 92.2 newtons. So once we then get our fx, we equal everything, we get ourselves 112.5. We then find our net forces in the x direction, which would be fx minus f coefficient kinetic friction. So 112 newtons minus 97, which I have to change to 92.2 by the right number. 92.2 newtons, which is then going to be equaling us, subtract over here, 20.3 newtons of force. That's going to be our net forces in the x direction. So now we can figure out what's our acceleration going to be. So since we have 20.3 newtons, it's equal to mass times acceleration. It's going to be F equals ma, force, mass times acceleration. Now this time we can use our weight of 400. You can see it here, 485. So we have this weight. We do need to figure out our mass still though. But all we have to do is just 485 divided by 9.8. Type it actually 45.9.8. We're going to get that our weight in kilograms will be 49.8 So now 20.3 newtons is equal to 40 kilograms times A. So we just divide 49. A is equal to 20.3. We're going to be looking at an acceleration of 0.41 meters per second squared. And since we're moving positively, we're going to have we're going to be speeding up. So that's our acceleration for part F. Let's go on to part G. Pretty much going to be asking us, a large box of mass M sits on a horizontal form. You attach a lightweight rope to this box, hold the rope at an angle of theta above the horizontal impulse. You find the maximum tension you can apply to the rope in order to make the box start moving at T minimum. Find the coefficient of static friction between the floor and the box. So we have to figure out what our seeing this glitch for a second, and it's confusing me. Okay, it looks fine. I don't know how this will pop up in the recording, but I'm gonna keep talking. On my side, it just looks like it's glitching. Anyways, so let's continue. So we have a box over here. We do have friction. Our friction is static this time. We have our normal. We have our weight. We have our force that we're pulling at. Our tension, which is minimum. So we need to pretty much figure out what our static is going to be. So we know that tension multiplied by cosine is going to be equal to the maximum static friction, which is also maximum static friction, is also our coefficient times our normal. So it will always be tension times cosine of theta, whereas we're just figuring out what our tension, minimum tension is. It'll be that right there. And then same thing, where tension minimum that we do times sine of theta plus our normal minus the weight is equal to 0. What we can always just do is relate these two similar to how we did in the beginning, in part A. So we know that this is equal to that. What we can do, for that, we move all this over, so N is equal to our weight minus our tension minimum times sine theta. So equal to weight minus 10 times sine theta. And then we equal them together. So T minimum times cosine of theta equal to our coefficient of static multiplied by N, which our N is also equal to the weight minus our tension minimum sine theta. So all we have to do now is just divide this over to the other side, and we can figure out that the way to find our coefficient of static friction is equal to the tension minimum times cosine theta divided by the weight subtracted by tension minimum of sine theta. And that's going to be our answer for part F, or part G, because it's just asking us what variables and what formula are we going to use to be able to find our static friction. That'll be it. We'll just be multiplying our two different directions, which is we're working in theta, to then make this work. And that is it. Thank you very much for watching.